The song you are listening to is being played in reverse. What is the title of this song and the name of the artist who created it? Big number of humans got that question right, but only a small number of audio models did. Today, I am going to talk about how we found these kinds of questions and show that our new dataset AUDITA is more challenging for today's audio models. Most existing audio tasks focus on recognizing what is present in the audio. Take this example from Kurdydyk. The question is, transcribe the speech.
Mr. Quilter is the apostle of the middle classes.
This is a classic speech recognition task. The model doesn't need to understand who is speaking, what the speech infers to, or any broader context. Here's another example from Open Audio QA. The question is, what sound is this? This is a sound classification task. The model only needs to recognize an acoustic event such as a dog barking, a siren, or an engine. These tasks are important, but they are fundamentally recognition tasks. AUDITA asks a harder question: do models understand audio, not just transcribing speech, not just detecting a dog bark, but identifying songs, movie themes, fictional characters, environmental context, cultural reference, and other auditory cues that require connecting sounds to real-world knowledge? For instance, consider a question from AUDITA. Across the audio clips, identify the artist and determine what shared surname links them. The answer is Jackson. Here, the task is not just to recognize each artist individually, but to infer the shared relationship between them. Humans are incredibly good at audio trivia and reasoning. This example from AUDITA asks, who is this fictional character?
Well, there's this lady in our office who's retiring, and they were passing around one of those big cards for us.
Many people can immediately recognize this voice as Bernadette from the Big Bang Theory. Here's another example. What country is this national anthem from? Many listeners can identify it as India. More generally, people do this all the time. You hear 3 seconds of this song and instantly say, oh, that's Queen. You hear this movie soundtrack, that's Star Wars. Humans are strong at identifying knowledge from short audio cues. Current multimodal models struggle with audio trivia style reasoning. This leaves an important gap in evolution, and surprisingly, existing benchmarks often fail to expose that weakness. Most existing audio QA benchmarks are either synthetic, caption-derived, or heavily template-based. The key distinction is in the last 2 columns. Existing datasets typically ask questions derived from captions, such as identifying objects or event mentioned in the audio. AUDITA instead uses human-written questions designed to test reasoning, knowledge, and identification from audio. Models can often exploit textual shortcuts instead of actually understanding audio. For example, in Kurdydyk, we have a question, is there a dog barking? You barely need reasoning for that. In fact, under an item response theory perspective, such questions have very low difficulty parameters, meaning they can be solved with minimal latent ability, often without requiring meaningful reasoning over audio. Prior work has also shown that leaderboard accuracy can be inflated by such low discrimination or shortcut-prone items under IRT-style analysis. But humans don't experience audio understanding as isolated event classification. We recognize entities, themes, styles, composers, accents, environments, and cultural reference. AUDITA is a large-scale benchmark built from real-world audio trivia and auditory reasoning tasks. Let me walk through how it is constructed. We start from multiple data sources, including quizmasters, pavements, and audio packets. From these sources, we extract and collect raw audio-based questions written by trivia experts and shared online. Next, clean and normalize the questions, since many of these originally came in an inconsistent quiz bowl or trivia formats. Then we convert this into human-vetted question-answer pairs, ensuring the questions require meaningful audio understanding rather than simple pattern matching. After that, we generate multiple choice versions of the same questions to enable controlled evaluation setting. Finally, we evaluate both humans and models on these questions to measure performance gaps and reasoning ability. In total, this results in a dataset of 9,690 questions. Importantly, many questions are explicitly designed to require deeper understanding and auditory grounding, not just shallow audio tagging. Let's look at the kind of skills AUDITA evaluates. Unlike traditional audio benchmark, these questions require models to connect audio to entities, concepts, and background knowledge. For example, in the first question, Audio Flamingo fails to identify Mozart from this musical. In the second question, the model hears a movie theme and must identify the movie. The correct answer is Batman, but the audio GPT model predicts Harry Potter. We see similar failures in pop culture and environmental reasoning. In the third example, the model hears the voice of a fictional character. Humans recognize the character immediately, but Gemini predicts the wrong identity. While Quento audio fails on an environmental sound question. These examples reveal that the challenge is often not perception alone. Models may hear the audio but fail to ground it to the correct real-world referent. This grounding appears repeatedly throughout the benchmark. We asked a bunch of people to answer both existing audio QA dataset and AUDITA. Most audio benchmark report only on model understanding, making it difficult to understand how far current systems are from human capabilities. AUDITA is the first benchmark to provide a systematic human versus model evaluation, revealing a large and persistent gap between human reasoning and current audio language model, and not by a little. In free-form settings, the difference is 23%. Even in multiple choice, where random guessing is 25%, models perform only at 15.6%. That means they are systematically attracted to plausible but incorrect answers. But accuracy doesn't tell the full story. We also use IoT to discover things like bad questions with annotation errors or useful questions that discriminate highly skilled humans or systems. See the paper for more details, but for example, models collapse rapidly on harder auditory reasoning tasks while human remains much more robust. Building on IoT model, we can now analyze where models succeed and fail in a structured way. By estimating difficulty, discriminability, and feasibility, we can go beyond raw accuracy and identify what kinds of questions first break the models. This reveals three major failure modes. Some failures occur on items that IoT assigns high feasibility but require domain knowledge, indicating missing world knowledge rather than perceptual issues. Another class corresponds to items for which even low difficulty questions fail, suggesting issues with basic audio perception or recognition. But the most interesting category is audio grounding failures. The most striking pattern emerges from IRT even when questions are highly feasible and discriminative models still fail when they must map audio signals to real-world reference. This gap turns out to be extremely large. To wrap up, AUDITA finds the kinds of tricky questions that humans are asking each other using audio and shows that computers aren't matching humans at that level yet. So if you're interested in audio reasoning, try your hands on this dataset. But we don't think this is it. We are hoping to create trickier questions in the future that better distinguish human versus computer skill, testing cultural, spatial, musical, and linguistic understanding.